Today I discuss one important topics. Obviously, one easy topics, and obviously all are familiar with these topics. We start from vector space, okay, or that means we know about linear space and vector space. We start from these vector spaces. In previous class, we also discussed vectors, scalars, and obviously parallelogram law. And obviously, when two vectors are parallel, and obviously we discuss a line passes through two. That means a line passes through two points. We also discuss, and obviously we also discuss that portion. That means a plane passes through three non-collinear points and this type of problems, okay. So we also discussed in previous class. Today we start from vector space. We write the definition of vector space first, okay. Or are familiar with this vector space, okay. So we first start from definition of vector space, okay. A vector space or a linear space, a vector space or a linear space or linear space, okay. V over F, V over a field F over a field F, okay, consists of a set consists of a set on which two operations okay, called addition and scalar multiplication, called addition and scalar multiplication, okay, respectively. Are defined so that, okay, are defined so that for each pair of elements x and y, for each pair of elements, okay, x and y in V, there is a unique element, there is a unique element x plus y, okay, there is a unique element x plus y in V, and for each element a in F, and for each element a in F, okay, and each element x in V, and each element x in V, okay, there is a unique element ax, there is a unique element ax in V, Okay, Ax in V such that the following conditions hold. Such that the following condition hold. Following condition holds. Okay. First one, V is 1. Okay. V is 1. That means for all xy in V, okay, x plus y equal to y plus x. That means commutative for addition. Commutativity for addition. Okay, commutativity for addition. Now we erase that portion and going to further discussion of that. Okay. Now second, B is 2. Okay, we write in this way: for all xyz, for all xyz in B, okay, x plus y plus z equal to x plus y plus z. Okay, this one is associativity of addition. Okay, next V is 3. There exists an element in V. There exists an element. There exists an element in V denoted by 0. Denoted by 0 such that x plus 0 equal to x. Okay, for each x in V, for each x in V, V is 4. For each element x in V, for each element x in V, okay, there exists an element y in V. There exists an element y in V. An element y in V. Okay, such that what x plus y equal to 0. Okay, now V is 5. For each element x in V, for each element x in V, okay, 1 x equal to x. V is 6. What that means, we talk about that here. For each pair of elements A, B in F, for each pair of elements, for each pair of element AB in F. Okay, AB in F and each element X in P and each element X in P. Okay, here ABX equal to A of BX. Okay, now we erase lower portion and going to further discussion of that. That means V is 7. V is 7. Okay, for each element A in F, for each element A in F, okay, and each pair of elements X, Y, and each pair of elements X, Y in V, X, Y in V, okay, A X plus Y equal to AX plus AY. V is 8. Okay, for each pair of element, for each pair of elements AB in F, elements AB in F, and each element X in P and each element X in P. Okay, here A plus BX equal to AX plus BX. Okay, now we also then erase that portion and going to further discussion of that. Then we also discuss then 8 properties which satisfies one vector space. Okay, then the elements X plus Y and AX are called the sum of XY, the sum of X and Y and the product of A and X, the product of A and X, okay, respectively. Now we also discuss another portion, okay, which portion says that means the element of F, we write it in this way, the elements of F, okay, are called scalars, okay, and the elements of the vector space V and the elements of vector space V are called vectors. Okay, and we also discuss in this way every vector space as a vector space over a field F. Okay, so every vector space as a vector space over a field, as a vector space over a field F, over a field F. Okay, now we also going to discussion of some person, that means an object of the form, an object of the form. Okay, here a1 a2 dot an. Okay, where the entries a1 a2 an are elements, where the entries a1 a2 an are elements of a field F, are elements of a field F. Okay, is called an n tuple with entries from F. Is called an n tuple. Is called an n tuple with entries from F. With entries from F. Okay. Now we also discuss that portion. Okay, that means, and this one are called n tuple, and obviously a1 and a2 an are entries or components. Okay, then we also going to discussion of that example. Okay, some example related to this vector space. We also write this definition of vector space. Now we're going to some basic examples of vector space. Okay, we also erase that portion and going to discussion of basic examples now. We write here example. Okay, first, the set of n tuples with entries from a field F is denoted by f to the power n. The set of all n tuples with entries from a field F, with entries from a field F, okay, is denoted by f to the power n. Okay, and obviously we marked as in this way: if u equal to a1 a2 an, okay, and p equal to b1 b2 bn belongs to f to the power n. Okay, and c belongs to f. Then what happened? Then u plus v equal to a1 plus b1 a2 plus b2 an plus bn. Okay, and cu equal to c of a1 c of a2 c of an. Okay, then what happened? then this one obviously we talk about that means if n, okay, if n be a vector space with respect to that means over f, okay, that means if n satisfies vector space, okay, if n satisfies all conditions of vector space with respect to this addition and multiplication, with respect to this addition and multiplication, scalar multiplication, with respect to this addition and scalar multiplication, okay, then what happened? Then if n be vector space over f, okay. Next we're going to discussion of, that means some matrices, okay. So it is that portion and going to discussion of some matrices, okay. So it is that portion now and going to discussion of some matrices first and then example of matrices related vector space, okay. An M cross N matrix, with entries from a field F, with entries from a field F, okay, is a rectangular array of the form, is a rectangular array of the form, okay. Here a11, a12 dot 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 a1n, a21, a22 dot 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 a2n, and here am1, am2 dot 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 amn, okay. Here each entry aij is an element of F, where aij belongs to F, okay. And obviously the entries aij, okay, with I equal to j, the diagonal entries of the matrices, okay. And obviously we talk about that the entries, okay, the entries ai1, ai2 dot 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 ain, okay, and compose the ith row of matrix, of the matrix, okay. and the entries A1j, A2j, A1j, A2j, AMJ be the jth column. Okay, or here we erase that and compose the jth column. Compose the jth column of the matrix. Okay, of the matrix. Then what happened? Then we also going to discussion in later. Okay, we erase that portion and going to discussion another example of vector space. Okay. Example 2. The set of all M cross N matrices with entries from a field. The set of all M cross N matrices with entries from a field. Okay. From a field F is a vector space. Okay, is a vector space with the following that means with vector space and denoted by M cross N if, okay, over F with the following operation, with the following operation of matrix addition, with the following operations of matrix addition and scalar multiplication. Okay, what is that? We take about that here. Okay, what that means? A plus B ij equal to Aij plus Bij. Okay, and C of Aij equal to C of Aij. Okay, for 1 less than equal to I less than equal to M and 1 less than equal to J less than equal to N. Okay, in this way we also discuss these. Okay, we also discuss these addition and scalar multiplication. So next we also going to further discussion of another example. Okay, another example we marked as 3. So we start from those polynomials. Okay, that means let S be any non-empty set. Okay, S be any non-empty set, and if some field, if be a field Okay, then what happened? Let if is if denotes the set of all functions, denotes the set of all functions, okay, from is to if, from is to if. Then what happened? Then obviously that means these two functions f and g in f is if are equal if is equal to gs. Okay, for each a is belongs to s. So we erase our portion and going to further discussion of that. Okay, denote the set of all functions from is to if. Okay, then what happened? Then the set, okay, the set if is if is a vector space, is a vector space, okay, with the operation of addition, with the operation of addition, and scalar multiplication, okay, defined for if g belongs to this if is if, okay, and c belongs to f by f plus g is equal to f is plus g is, and cf is equal to c of f is, okay, for each is belongs to this is, okay. Now we also discuss 3 examples, and obviously this one are all vector spaces, okay. This one are all, that means vector space, and obviously so many examples are laid to discuss that vector space, okay. So today we also discuss, that means vector space, and related some example, okay. So if you get this type of videos, please subscribe my channel and follow my videos, and obviously if you gives like, please click on like option, and if you have some question, comment, suggestion, please write it in comment box. So today I stop here. Thank you.